Presentation is divided into three parts. In the first part, I'll talk about useful substances that can be extracted from algae. In the second part, I'll explain a little bit membrane filtration, which is a technology we are suggesting for using in this extraction process. In the part three, we will present an extraction method for DHA, also extraction of DHA from algal biomass in a membrane contactor. So let's start on part one. Also, algae, as other plants, consist of macro and micronutrients. Macronutrients are proteins, carbohydrates, and lipids. The micronutrients, vitamins, minerals, pigments. But those proteins can also have some functionality. So we have bioactive peptides, essential amino acids. It could be also single amino acids. Carbohydrates, we have bioactive carbohydrates or polysaccharides, such as alginate, carrageenan, fucoidins, or laminarin. Lipids, there we can mention DHA and EPA. We have also mentioned pigments, vitamins, and minerals for micronutrients and others. So we can explain peptides, bioactive peptides. For example, those are the peptides which consist of 2 to 30 amino acids. There are some beneficial properties with these peptides. In the literature, one can find that they are anti-hypersensitive, antioxidant, anti-thrombotic, antimicrobial, and they can be they can possess immunomodulatory properties. Food for specified health uses. This is the Japanese organization, has approved 2 products which has anti-hypersensitive claims. This is Wakame peptide jelly or noripeptide S. So when it comes to bioactive polysaccharides, alginate, it contains of manuronic and glucuronic acid units. Normally it's used as a thickening agent, encapsulating agent, dietary fiber, weight management can be controlled with alginate. Generally, it is a GRAS substance, which means generally recognized as safe. Carrageenan consists of galactopyranose units. It is also thickening agent, gelatin substitute, fat substitute. Here, there is also claims about health benefits with carrageenan, but also in recent years, there were some negative properties related to carrageenan, so therefore I haven't digged deeper into these functional effects. But it's still on the GRAS substance list. Fucoidins can be, they consist of fucopyranosyl units, antiviral, anticoagulant, anti-cancer, osteoarthritis they can be used for. It's also a GRAS substance. Laminarin consists of beta-D-glucose molecules with anti-inflammatory properties, anti-apoptotic, anti-cancer, anti-probiotic. It's also a dietary supplement. I didn't find it on GRAS substance lists, but I assumed also probably belongs there. So pigments, we can mention astaxanthin and fucoxanthin. There are xanthophile carotenoids. This xanthophile just means that they are carotenoids that contains oxygen. Health benefits related to astaxanthin, for example, antioxidant, inhibits lipid peroxidation, anti-inflammatory, anti-diabetic. It's sold as a dietary supplement. But for example, here in Norway, it's used to make farm salmon pink. Fucoxanthin, health benefits are antioxidant, anti-obesity, anti-inflammatory, hepatoprotective. It's also a dietary supplement. So I've added some references here. So at the end of the presentation, one can see this 4 and 5 number in the superscript. One can find some publications that are related to these claims. And bioactive lipids, as mentioned, DHA and EPA, both of them are omega-3 fatty acids. Health benefits, anti-inflammatory, reduces heart disease risk, slows cognitive decline, slows degeneration of the retina. There are also pharmaceutical products, so products, so Lovasa, Pnova, Omacor. So all three of them contains both DHA and EPA actually. So this E in front of DHA and EPA means that they are ethyl esters of these fatty acids. EPA has similar health benefits. Here we have mentioned some others, some lowers triglycerides and non-HDL cholesterol. Improves endothelial function. It's anti-thrombotic. And there are two products which are registered as pharmaceutical products. So Eskepa and Eparel, both of them contains only very pure EPA, also ethyl ester of EPA. So in the part 2, I'll show you a little bit about this membrane separation technology. So it's actually what Duemilio is about. We are designing those systems for various applications. So in this slide, at the beginning, it is important to explain the difference between dead-end filtration and cross-flow filtration. Dead-end filtration is just conventional filtration method, while cross-flow filtration is what we use in the membrane filtration technology. So as one can see on the dead-end filtration, the flow is perpendicular to the filter. Smaller molecules or particles will pass through the filter and the larger will be retained. So then the residue is created. When this residual layer is at a certain thickness, then the filter is clogged and it needs to be discarded. But in the cross-flow filtration, cross-flow exerts a shear stress on the surface of the membrane in the tangential direction, which removes buildup of residue from it. So in this way, the membrane can last a filter for much longer time, and this can also be washed. So that is normal, for example, for ceramic membrane can last for 7-8 years. what is also important to mention here that these membranes has different pore sizes. So they can, for example, if we go from the left to the right, then we have microfiltration in the range of 0.1 to, yeah, let's say 5 micron, but it could be above 5 as well. What we filter there, or what is rejected in such type of membrane system is, for example, bacteria, yeast. When we're talking about algae, it could be alginate, carrageenans. Then we have ultrafiltration, which is in the range from 0.01 micron to 0.1 micron. Or here we can also use probably kilodalton from 15 to 750. And what's normally is filtered there is viruses, proteins. When it comes to algae, probably fucoidins, alginate as well. Because here it depends on the size of the polymers and the molecules, which separation system one will decide to use. So nanofiltration is down to below 0.01 micron. We can say from 0.2 to 15 kilodaltons. This membrane will reject the multivalent ions, short peptides, for example, laminin, astaxanthin, fucoxanthin. And what is the finest is the reverse osmosis. Basically, reverse osmosis rejects everything except water. Monovalent ions, sugar, single amino acids. So it's that's also something used for desalting seawater, for example, to create drinking water from or purify water in general. So this is important, which means that we need to bear in mind that these systems, when we want to separate something by using a membrane filtration, then we need to think of the molecule size, particle size, so what we are going to separate, and then we select the system. It could be a one, for example, it could be a combination. For example, ultrafiltration, nanofiltration, or it could be a micro, ultra, nanofiltration, or all of four. So it depends on the application. So here I was just shown the ultrafiltration, which is with ceramic membranes. So in the picture in the middle, we see that the feed flow under pressure is applied through the channels in the middle, and then what passes through is called retentate. But since pressure is applied, then we will be able to squeeze something through these walls of the membrane, which is actually the filter. So that is called permeate. So that is important, that pore size of these membranes and what will follow with the permeate. If it is an aqueous solution, then what will follow with the aqueous solution when we press this through? It depends on these pore sizes or type of membrane we will use. So on the right side, it's a picture of an ultrafiltration unit, which consists of, here is the 10 houses shown, and each of them contains 37 of these membrane elements. So it means 370 total. Here at the bottom, left bottom, is shown that they can vary also by number of channels, size of channels, these membranes, in addition to pore size. So all this is just to increase the area of the filtration area. So on this slide, we'll just show that these membrane filtration systems, they require other things around equipment. So I'm not going to particularly explain every of these processes. It's just to show that, for example, the Duemilio has proprietary technology in fish protein isolation, where we can use stick water or hydrolysates to isolate protein, and then we use membrane filtration after tricanter before any evaporator. Then we can purify oil, remove PCBs, PTBs, dioxins, and then we have this DMEGA technology, where is actually the extraction of or up concentration of DHA from algal biomass. So that's the technology I'll be talking about later. So possibility, as advantages of this membrane filtration is the possibility to achieve a high mass transfer surface area with the relatively small installation dimensions. Membrane separation doesn't require heating, which saves energy compared to other methods, for example, evaporation. It doesn't require chemicals in operation, but we need some chemicals to clean these membrane systems. Both permeate and redentate can be used for further processing. So if we go back to this image, so here retentate is also liquid as the permeate, which so both of these liquids can be utilized in further processing. So it's also flexibility because it covers a wide range of applications. So in the part 3, so go to the part 3, we'll demonstrate the extraction of DHA from algal biomass with using the membrane contactor technology. So this was done in the 4 experiments. So experiment 1 was a chemical hydrolysis was tested against enzymatic hydrolysis. So chemical hydrolysis is much better. It extracts 70% more C22, 6, 30% C18, 1, and 24% more C16. And the pre-treatment with proteases didn't improve free fatty acids in enzymatic hydrolysis. So chemical is better, but for chemical will just hydrolyze everything. So we will see later that when we have tested hydrolysis efficiency of the 4 commercial available microbial lipases, then I'll just say abbreviation here because these names are hard to pronounce, as a CR, MG, and PS, and liposome LP-STAT. It showed that MG was preferentially releasing saturated fatty acids and monosaturated fatty acids, while PS released preferentially polyunsaturated fatty acids such as DHA. So this led to the experiment number 3, where we did fractionation of fatty acids in a membrane contactor by simultaneous enzymatic hydrolysis. In experiment 4, we just tried to dewater this algal biomass using microfiltration, so it was also successful. But I'll present experiment 3 because it's probably the most interesting to show. So this method was done in 3 stages actually, or 1 pre-treatment stage and first stage, second stage. So I don't go into details on all of this. It's shown here, so one can look further into these details. But pre-treatment is just that algal biomass is suspended, then it's heated, cooled down, and then enzyme phospholipase is added, incubated for 2 hours under steering, and then cooled down. Then in the first stage, so what is important here, that in the first stage, we add Mg lipase, which is preferentially, as we said, saturated fatty acid. So this stage removes saturated fatty acids. While the second stage, we use pseudomonas lipases, or here is the mistake, it should be PS, so it's PS lipase is added, and this one removes DHA because it's preferential towards DHA. Just to illustrate this process, we have this figure here. So on the left side, so okay, if we start with the middle, then we have this broken line in the middle is represents the polyimide membrane. On the left side, we have aqueous solution. On the right side is the organic solvent. So in all this hydrolysis happens in the aqueous phase. So there we can have the triglycerides, enzymes, glycerols, DHA. But what happens when this aqueous solution circulates on the left side and the organic solvent circulates on the right side, then through these pores, membrane pores, free fatty acids will pass into the organic solvent. And those solvents are not mixed. When one have a proper speed, liquid flow, and so they don't mix. So that what only happens is that lipophilic substances, they are passing from aqueous solution to the organic solvent, or in this case we were using hexane. So when we use, for example, Mg lipase, then we are removing more of the saturated fatty acids. When first stage is finished, then we just take the solvent and replace. So takes a solvent that contains saturated fatty acids, and then replace with the new one, and start second stage extraction, where preferentially DHA is extracted, because then we use PS lipase. Okay, so I hope that this one is clear. So here the results are here shown graphically as well. So we have on the left side is a DH graph, on the right side is a palmitic acid graph, which is saturated fatty acids. So we see that the graph is divided in the first stage and the second stage. So DH in the first stage, we can see that its graph is much lower than the graph in the first stage for palmitic acid. So which means that palmitic acid in the first stage is, so this is the concentration in organic phase on this side. So there's, so the concentration is much higher for palmitic acids than for DHA. And then in the second stage, we see that actually here we have the DHA and the palmitic acid is approximately the same. So in this way, we are able to up-concentrate DHA in the solution. Then instead, if we were using just, for example, this enzyme that preferentially releases saturated fatty acids. Advantages of the membrane conductors are also flexibility and dependent control of fluid flow rates, no emulsions, no flooding at high flow rates. It doesn't require density difference between liquids. It's also scalable, linear scale-up, modular equipment, possibility of integration into an existing process, compact design consuming less energy, and elevated mass transfer rate. So literature says that it's 500 times larger contact area per unit volume than conventional liquid extraction columns. So conclusion for this experiment is that membrane contactor technology can effectively be used in up-concentrated DHA from enzymatically hydrolyzed algal biomass. And so the overall conclusion is that algae are a valuable source of nutrients and bioactive substances that could be a part of healthy, functional diet for farmed animals and pets as well for humans. And membrane filtration separation technology can be applied as an effective tool in extracting useful components from algae. So here I've also left some literature. For those who are interested, they can go through this and find more information on certain topics. And we have Milieu is a part of Eagle Group, so there are other companies involved. Brena Quality Group, Therma, Eagle Technology. So Brena is also using membrane technology to purify, for example, slope water, processed water, and oil. And thank you for your attention.